On the last video, we talked about experiments. And experiments are important for science because they result in what we call empirical data, where you can make a conclusion that A is causing B. There is a relationship of causation between the independent variable and the dependent variable. In other words, that the independent variable is the cause that creates the effect on the dependent variable. And that there are no other factors or confounding variables which are causing this. And to make sure that the independent variable is causing the outcome on a dependent variable, you have to have what we call a control group, where you compare doing something to not directly doing something to see if there's a change on difference between the two groups. If the experimental groups change more than the control group does, then you can tell for sure that independent variable did something. But you can only do that if you held everything else constant at the same time. That means only the independent variable changed between the control group and the experimental groups. All the other variables were held constant. That is what we talked about in the last video. And we also talked about the 5 basic parts of the experiment, which are the independent variable, the dependent variable, the constants, the control group, and the experimental group. And we also talked about the fact that you have to go through the first steps of the scientific method to successfully set up an experiment. You have to ask yourself the question, put it into a problem statement. You have to do the research of the background so you can understand the independent variable, the dependent variable, the constants, the relationships that exist between these variables, the importance of having a control group and the experimental group, and what's going to happen at the different levels of the experimental group compared to the control group. Then you're ready to set up the experiment by establishing how you're going to change the independent variable, how you're going to measure the dependent variable, what's going to be your control group, what are going to be the levels of the independent variable that you're going to have in the experimental groups. Are you going to have the safety or ethical protocols in place, and how are you going to increase reliability and validity? And that's what I wanted to spend this video on, steps that scientists do to increase reliability and validity. Now, the first thing is to make sure you keep everything constant. Now, I know that we already talked about this, but make sure that when you have an experiment, only one thing is changing. Keeping the other variables constant is important to make sure that the change that happened to the dependent variable or responding variable happened because of the manipulation that you did or the change that you created in the independent variable. That means that to establish that causation, I have to make sure nothing else is changing, that there aren't other factors or confounding variables which are creating that. So you keep things constant. The control group is also important because if you change the independent variable without comparing it with a group where you don't do it, then you can't be sure that what you saw was because of what you did. We talked about for example, this thing that's in the screen here. If you put several types of fertilizer in the plants and you're going to measure how much they grow, but you didn't have a control group where you put no fertilizer, then you can't say the plants are growing because of the fertilizer. Because if the control group, if you had one, had grown just as much, then the fertilizer would have made no difference. But without the control group, you would never be able to tell you that. So you always have to make sure that you have that. Otherwise, you cannot say the independent variable is what caused the change. You know, for example, if you have a chair in a room and this chair is shaking like crazy. Well, of course it's shaking like crazy because you're in the middle of an earthquake. And then you say, well, the chair is shaking because of the earthquake. Well, you can't really say that unless you've seen that same chair not shaking when the earthquake was not happening. Because what if that chair has some sort of mechanical device on it that makes it shake? Right? So you can't say that something causes something else unless you've observed it without that thing there. Alright? Another way to increase the reliability or the validity of an experiment is to use some other techniques which we're going to talk about very quickly now. Now, one of them is called a placebo. Now, you see here these medications that you have on the left side. Now, placebos are really cool. Let's say you're doing an experiment and you want to find out if a medicine helps someone with a certain disease. If you see, let's say if this makes a person happier. I'm depressed, this medication is going to make you happier. Now, is the medication actually making you happier, or is your belief that the medication is going to make you happier is what is actually making you happier? In other words, just because you believe it's going to make a difference, sometimes it does. A lot of things are like that. You go to these internet scams and they say, oh, this medicine is going to make you have more energy. Then you take that and you feel full of energy. Well, is it really the medicine or the vitamin that you took, or is the fact that you believe it's going to make a difference, that it actually makes it happen. So to solve the problem in psychological and medical studies, what they do is that they give people fake medicines, sugar pills. So they have, on the experiment, they have 3 groups of people. Someone that doesn't get the medicine, someone that gets the medicine, and then someone who thinks they're getting the medicine, but they're not really getting the medicine. If there is no difference between the people who took the real medicine and the people who think they took the medicine, then it wasn't really the medicine that made the difference, it was the belief that made the difference. So that's why placebo exists. Now, another cool thing that sometimes people do is called a blind study. In science, there's always a problem that the fact that you're studying something can actually change the thing that you're studying. So, for example, the researcher, knowing that he wants to prove that the medicine is working, inadvertently does things to bias the patients so that the patients will believe that it's working and perhaps it starts working better. So, to make sure that the researcher doesn't bias the data, to make sure that the researcher doesn't purposely treat one patient better than somebody else, I know like, oh, this patient is not getting the real medicine, I'm sure he's not going to do as well. And that belief makes the patient be treated differently, and then he ends up being different than the other patient, not because of the treatment, but because of the treatment, of the way the doctor acted with him. To solve this problem, you have what is called a blind, where the researcher doesn't know who's taking the real medicine and who's not. He will take care of everybody the same because he doesn't know who's actually in the study for the experimental group and who's not. So the blind is when the researcher doesn't know if he's an experimental group or if he's not an experimental group. Now, on a double blind is when you have that and a placebo at the same time. So that means that the researcher and the person who's seeing the experiment both don't know who's in the experimental group and who's not. So only a lab tech somewhere that's not the main researcher will have the information, and that's only going to get revealed after the experiment is concluded. So only after the researcher is going to have access to the information about who was a placebo and who was the real and who was not, and the patients themselves, only after will they find out if they took a real medicine or a placebo. That's called a double blind, when you have the researcher doesn't know who's in a group or not, and you also have a placebo at the same time. These things are great because they make sure that their results are valid, Another important thing to make sure that your experiment is valid is to use proper sampling techniques. The thing is that when you're studying something, usually the population is too big for you to examine everybody. Let's say, for example, you want to find out if a certain medicine will make your cardiac problems better. If it's going to reduce, say, for example, the cholesterol that you have in your bloodstream. All right? So ideally, you would go to every single person that had high cholesterol in the world and give them the medicine, and then some will get a placebo, some will get no medicine, and some will get the medicine. You sort them in groups or whatever. Maybe you do a double blind, whatever. But ideally, you would test everybody, but practically, that's impossible because it costs too much money. You would never find the people. You can't do it. So what you got to do is you got to take a sample of the population when you're only going to measure a group out of the whole. But when you do that, you got to make sure that the sample truly represents the population. That means that you have to sort the people correctly. You have to get the people from the population in a way that's not going to bias the data. I'm not going to look at only the males or only the females, or I'm going to look at the population that actually represents the people that I'm talking about here. Now, once that's actually done, it's also important to make sure that your groups, your experimental group, your control group, your placebo group, whatever groups you have, are equal. By that I mean, for example, what if you have a control group that's healthier than your experimental group? And then you can't tell that the control group did better, and you're going to say like, oh man, my medicine doesn't work. Well, maybe it wasn't the medicine. Maybe the control group had something special about them. So that means that after you take the sample and you're getting these people into the groups that you're going to use in the experiment, it's important that you randomly choose where the people go. Or that you set up the groups in a way that you're going to make sure that they're not going to be misrepresenting the population, that every group on the experiment is equal or equivalent. And then the best way to do that is to randomly sort the people into the groups. A good example of what I'm talking about, let's say, for example, if I have a classroom and I want to find out, if a certain method of teaching is better than another method of teaching. And so what I do is I set up groups in the class, and I'll treat the people in the class differently. But when I'm setting up the groups, I have one group that's all the best students, and one group that's all the bad students. You know, and then I say, oh, see, this technique clearly works better. You know, these kids did better. But was it because they were better students, or was it because the technique was actually better? So that means when you're comparing something like that, you got to make sure your groups are equivalent. You have to randomly sort the people in the classroom into the groups to make sure they're equivalent. On the next video, which is a bonus video, you don't have to actually watch it, we'll talk a little bit more about sampling techniques and other ways to make sure that the research that you're doing is a little more accurate. And they're advanced. It's not, I don't want to require you to know. But do know that researchers often do random assortment to make sure that their groups are going to be equivalent. And sometimes they even do what's called stratified assortment. And that's when, for example, if they know that they want specific groups to be in their group. For example, I want every group to have an A student. I want every group to have a B student. And I want every group to have a C student. So what they would do is they will randomly assort people, but they will make sure that that in the groups, these things are represented. That's called stratified assortment. And you would do that when you want to control the assortment a little bit more. But you got to make sure that that's truly represented population and that there's nothing special about the people who got selected for those seats. Another thing you can do to make sure that your groups are sorted well and that they're equivalent is that you can test them before you do the experiment for the dependent variable. In other words, you do a pre-test to make sure that their groups are equivalent before you actually expose them to the treatment, and then test them after to see the difference, what happened between the two groups. Sometimes scientists will do that as well. Another way to increase the validity of an experiment, and every good design should have this, is to repeat your experiment. Now, of everything that I said, this is perhaps one of the most important things. After having constants and having a control group, more important than anything else is to repeat your experiment. Because, and by this is different from replication, where other people do the same experiment you did again to make sure that you did it right. This is talking about when you're actually measuring things, measure it more than once. That makes take multiple measurements or repeat the entire experiment several times. Whatever way you want to look at it, do the experiment again. So that means, for example, if I'm measuring, if I want to find out if this medicine actually works, I don't want to give it to one person. I give it to many people, and I take the average of those people. If I want to make sure that this enzyme will speed up the reaction, I won't just do it once. I will do it several times and get the averages to make sure it works. So always have multiple measurements. And throughout the year, when you design your experiments, ensure that the data is trustworthy, that it's reliable by having these multiple measurements. And also, the last thing I want to talk about is that when you're developing an experiment, make sure that you use the best tools and methods available at the time. Because if you think, for example, you want to measure something like a time interval, you can use a wall clock, you can count it on your head, or you can use a stopwatch. Which one is the best one to use? Well, of course, the stopwatch, because it's more precise. And it will give you a data that's more close, so you work with those numbers better. So use the best tools you have to measure your dependent variable and to manipulate your independent variable. Use the best, simplest, most straightforward research methods possible to reduce experimental errors and human error when you're actually doing the experiment. So as you can see, setting up an experiment is not an easy task. You've got to make sure that you have those 5 basic parts. You've got to make sure you have constants, a control group. You might even want to add extra things like placebos and blinds and double blinds. You've got to make sure you sample correctly. You've got to make sure you sort the groups correctly. You've got to have repetition. You've got to have good tools and good techniques. So it takes a lot to be able to do that. So to design experiments, it's very important to have what we call creativity. It's very important to use that creativity that we talked about before in this lecture series, because creativity is what's going to make you good at setting this up. So again, creativity is important here in science. And also important to remember that science is a multidisciplinary study, and that 2 different people can do the same kind of test in a different way. For example, if you ask someone about the video game thing that we were talking about, when it comes to measuring the satisfaction, a psychologist would give a survey, but maybe a biologist would look at the levels of endorphin or the chemicals, hormones inside a person's body, or maybe a neurosurgeon or a neurologist will look at the electrical impulses in a person's brain. So as you can see, there's a lot of different ways to go about answering this same question. And that's what makes science so diverse, because people from different backgrounds will study the same thing and then try to get their answers, like we talked about in the first video when we talked about evolution. All right, so that's how you set up a good experiment. I'll see you guys in the next video.